AA277. I'm Max Schwager. I'm going to be the lecturer. Art is in the back. He's the CA. Art took the class last year, did exceptionally well, so he'll certainly be able to help you through any questions on the homeworks or any conceptual problems or anything related to coming up with ideas for your quarter projects or whatnot. So the class that I see here is a bit larger than what I typically expect for AA277. This is really a kind of research seminar focused class. There's going to be a built-in component of discussions, and a major component of the class is a project, a research project. So typically what happens is we get a fairly large group at the beginning, and then a few people kind of, as they're shopping around for classes, drop out after the first week. And so we'll reassess the numbers at the end of the week or the beginning of next week and figure out where we are. So let's first talk about the kind of main components and structure of the class. And then for today, what I'm going to do is give you a presentation that kind of talks about the subject matter in the class, multi-robot systems. The main research topics in multi-robot systems, and my own lab. I run the multi-robot systems lab here at Stanford, so I'll tell you about some of the projects we're doing in my lab. And then we'll go through the syllabus in a little bit more detail. So everybody has a syllabus? I don't think I saw anybody come in who didn't have one. Okay, good. So let's turn to the second page in the syllabus. And I just want to talk through the main components in the class. You see the grade breakdown, homeworks, paper talk, course project, and so on. So these are the main things that we're going to be doing in the class. There's the homeworks. There's going to be a weekly problem set style homework, as you'd expect in an engineering course. However, these are going to be a little bit different than what you may have seen before. So there are going to be your syllabus back here. Art, let me give you these syllabi, and you can hand them out as... Oh, there you go. Sure. And you as well. And Art, do you want to take the extras and hand them out as people come in? Okay, so we'll have weekly problem sets. There'll be, maybe 3 or so mathematical problems related to the lecture material. And then there's going to be a paper. Every week we're going to have a paper to read. The papers are going to range from fairly recent, like the past 2 years, to maybe more like 10, 15 years old. And they're going to be chosen. They're not meant to be examples of excellent papers. They're meant to be patchwork. Like some have obvious flaws. Some don't appear to be that novel, but were enormously influential. Some were not very influential, but I think they're very novel. And so part of the homework exercise is to read papers and to think critically about them. So you guys will read these papers as part of your homeworks and write up a review on the papers as if you were reviewing them for a conference or for a journal. So all of you, well, I suppose all of you are either master's or PhD students. There might be an undergrad or two. Raise your hand if you are an undergrad. Okay, so you're all master's or PhD students. You're all plugged into research to one degree or another. And you should know by now that the main business that we're engaged in is publishing research. And publishing research means that not only do you write papers, but you review papers as well. That's what part of being a research community is about. And it's not something that you're born with, just knowing how to write a review for a research paper. So one of the main aims of this class is to give you all some practice in writing reviews and to look at research papers critically. Because, papers are written to be convincing, but it's a separate skill altogether to step back and remove yourself from the claims of the paper and consider the paper based on its merits in an objective way, and to think about, okay, these authors claim that they solved the world's hardest problem, but let's step back a little bit and see, did they really do what they said they did? Is that really the best way to do it? Are there other ways that could be simpler? Do their proofs really hold up? And so on. So to be critical about the literature. Every paper has a flaw, and even very flawed papers become very influential. So learning how to critique research is, a multifaceted and highly non-trivial sort of skill to obtain. It's a very much a skill, right? So one of the things we're going to do in this class is practice that skill. And so going along with that, every week we will have what I call a paper talk. And what that means is that by the end of the term, every single one of you will have led a discussion for a subset of the class on a paper for the week. And to do this in a way that promotes everybody to read all the papers in as much depth as possible, what I do is I select randomly from among you, maybe 3, maybe 4 students, and then we divide the class into 3 or 4 groups, and each of those students then leads a discussion among their group. And then we synthesize those discussions. At the end of the class, we'll all come together as one class, and kind of each group leader will highlight the main points of those discussions. So that means all of you should be ready at the end of the week to lead a discussion on the paper for that week. Does that make sense? So that's maybe one piece of this class that you may not have experienced in other classes. Those discussions will occur on Thursdays, and problem sets will be due on Fridays. So problem sets will be handed out on Fridays and then due the following Fridays. Of course, this week we won't have time to you guys have not read a paper yet, so we will not be doing a paper talk or a class discussion this Thursday, but starting next week we'll be doing that. So this Thursday or this Friday, the first problem set will be handed out. You'll have the first paper, you'll have an opportunity to read it, and then we'll discuss it the following Thursday. So take note that they're due on Friday, the problem sets, but the paper discussions are on Thursday. So given that you have some probability of being selected to lead a discussion on the paper at the day before the problem set is due, it pays to first read the paper and do the reviews, and then finish the rest of the problem set at, after you've done the piece that you'll be called upon for the discussion. Does that make sense? Okay. So then there won't be any exams, but in place of a midterm, what we're going to have is a project proposal, and that happens roughly in the middle of the course. You can see on the very last page of the syllabus, excuse me, there's a lecture by lecture breakdown of the topics and also the assignments and when they're going to be due. So the project proposal we have due on Tuesday, February 12th, which is roughly in the middle of the quarter. So we have 10-week quarters. They're really short, especially when you want to do a research project. So even though the proposal isn't due until halfway and the project itself isn't due until the end, you want to start thinking about projects and topics today. And you will have the option to do your projects in groups. You can form groups of 2 or 3. Exactly the maximum group size depends on the final head count in the class. So I'll tell you, count on something like a group of 3 max, and then I can give you a firm answer on the maximum group size later. So start thinking about who you might want to work on the project with. You're welcome to do a project on your own. The project, it's a bit of a chicken and egg problem, right? Because you want to start thinking about your project, but we haven't covered any technical material in the class yet. So you always want to be looking ahead in the list of topics. Do a little bit of research on your own. Google Scholar is very much your friend. So if you're not familiar with scholar.google.com, absolutely make yourself familiar with that. It's a beautiful search engine for searching the entire world of the research literature, not only in technical subjects, but just the whole universe of research. It's extremely valuable. So if you're interested in an idea that's connected to distributed algorithms or robotics or any of the topics that are involved in this class, type some keywords into Google, take a look on Google Scholar, see what's out there, and start educating yourself on the state of the literature. So in the class we have a textbook. Did I bring it? I didn't bring it, but it's listed at the bottom of the second page. Mesbahi and Egerstedt. Mesbahi and Egerstedt are both giants in this field. Mesbahi is at University of Washington. Egerstedt is at Georgia Tech. Their book is very clear, very beautifully written, very mathematically rigorous, graph theoretic methods and multi-agent networks. So I recommend that you get the book, but really the lectures are going to be quite self-contained. So it's a great secondary resource, and if you're doing research in an area that's in this universe, robotics and controls and, related to multi-robot systems or multi-agent interactions. It's a very good book to have. But it's not as if I'm going to be assigning problems out of the back of the book, and I'm not going to follow the book that closely. And we're also, in addition to the readings for the problem sets, there's also going to be paper readings that are listed along with the lectures in the list of topics in the schedule. So, and we're going to focus more and more on the current literature and taking lecture material from the current literature as we get farther and deeper into the course, right? So when it comes time to start thinking about your projects, we have all these papers listed in this list of readings in the syllabus, and also I have uploaded a number of papers in this research area in the Canvas website. They're all there. Browse through them, read the abstracts, look at the titles, and see what interests you to get the gears turning to think about projects. Okay. Any questions so far about organization and structure? The final project then is going to be due in the last week, and it's going to consist of a presentation, which it depends on how many of you are here. That determines the size of the time slot, but something like 10 minutes. And then a final report, which the parameters I'll give you those later, but something on the order of 10 pages. It's going to depend on the size of your group. So, if you don't have any questions about logistics and organization, let's get into some material. Yeah, June N.
Projects, proposals.
Yeah.
So 7 week, and then the project itself is due on the 10th week. So it's,
yeah.
I'm guessing it's going to be like simulations. As in projects will be simulation based, or will they have to be actual?
It depends on, simulations are fine, and the vast majority will be simulations. If you have hardware available to you through the labs that you're working in, you are very welcome to use hardware. So there are going to be cases of you where you're, multi-year PhD student, you already have hardware available to work with. Maybe a ground robot, maybe a multi-link manipulator, maybe an aerial robot. You're very welcome to use those platforms for the project, but it's absolutely not required. Simulation work would be expected. Theory work would be nice. Algorithmic contributions would be nice. Okay, so I'm going to have office hours. They are listed at the top of the front page of the syllabus. They're going to be Thursdays 11 to 1 p.m. You are welcome to come and discuss homework problems or the lecture content. You're also welcome to discuss project ideas. And I assume I'm going to see more and more of you as we get closer to the proposal deadline to discuss project ideas. Okay, so multi-robot systems. What is it? What are we going to be talking about in this class? So multi-robot control, communication, and sensing is the title of the class, but it's really control, communication, and sensing. So it could be, you could imagine lots of different ways of teaching this subject, and my core domain is really control and planning and optimization and that side of robotics. So the communication and the sensing part is going to be sort of communication models in service of control and planning, sensing models in service of control and planning. So we're not going to dive deep into vision, we're not going to dive deep into SLAM, we're not going to dive deep into networking protocols or MAC layers or any of that stuff. It's going to be about control. So let's talk a little bit about the kinds of problems that we'll be interested in this class. So, multi-robot systems, there are two ways to think about this. Why do we want multiple robots? Why are we interested in controlling multiple robots? Well, one reason is because in some application domains, multiple robots are better than a single robot, and I'll show you some examples. In other application domains, you, by definition, have to worry about multiple robots. It's not an advantage, it is just part of the problem. And so here's an example. This is not robots, this is humans, drivers. Let me make sure. Okay, the sound's off. This is human drivers in an intersection. I believe this is Hyderabad in India. There's apparently no traffic signals going on here, and if there are, nobody's obeying them. It's just a big mess of traffic, but there are no collisions. There are cars, buses, bicyclists, pedestrians, no collisions. So this, if we want to have autonomous cars, lots and lots of autonomous cars that drive in places like Hyderabad, we're going to have to be able to do this autonomously. And this is the kind of problem we're going to be looking at in this class. We call this collision avoidance, multi-robot collision avoidance. Organisms in biology are very good at doing this, right? Birds don't run into each other very often, and if they do, they don't hurt themselves when they do. Maybe they flick wings a little bit, but you don't have full-on collisions with birds usually. Swarms of insects, they usually don't run into each other. People walking around on the street, maybe you brush a shoulder, but you don't smack full-on into one another. So there's lots of lessons to be taken from biology and multi-robot systems. Here's another example, if I can get my pointer to work. So something that is a kind of an emerging trend in the research, something that we're working on quite a bit in my lab, is competition in multi-robot systems. So this is drone racing. This is what's called a FPV league, First Person Viewer League. These are quad-rotor drones. I suppose you guys are all familiar with this quad-rotor drone platform. They have a camera on the front, and what you're seeing is the field of view of one of the cameras on a drone. Now these are fully human piloted, so the human wears a set of goggles, they get a video feed, and they have an RC controller, and they race the drones with this using the video feed. So this is a multi-robot problem, I claim. Not only a multi-robot problem, it's also a problem in perception and a problem in avoiding collisions with static obstacles, but it's more than that, it's a problem in competition among multiple robots, because the robots do interact here. You can see, well, you saw, I think, that when the robots first took off, there were multiple drones that were racing, and they were interacting with one another. They were blocking each other. The guy behind was trying to pass to the guy in front. And so there's a whole strategy in the interaction among these robots. Again, this is something that human pilots do very well. This is something that animals do all the time, competition in the wild. But it's something that it's very hard to create an autonomous system that does this. So let's think about a couple of other applications. So the ones I just gave you were kind of a non-cooperative application, collision avoidance with autonomous cars or autonomous vehicles, and then a full-on competitive application, which is drone racing. There are lots of other examples where cooperation is key. So for example, a prototypical application would be cooperative environmental monitoring. Suppose you have a group of robots. These are our little robots. And suppose we are hired by a science operation, and the scientists want to study a forest. So we give our robots to the scientists, and we want to have these robots endowed with some capabilities that allow them to do monitoring over a forest. So what might those capabilities be? Well, one would be deployment. We want the robots to move out and cover the forest so that all of the important parts of the forest are being monitored by at least one robot, for example. Another would be adaptive sampling. So the robots might want to figure out, based on their online measurements, where the interesting stuff is happening in the forest. Maybe we're interested in forest fire risk. So maybe the robots first spread out and they start looking and they say, oh, there's a lot of moisture over here, and there's not a whole lot of dry brush, but over here it's very dry and there's a lot of extra brush on the ground, so we're going to concentrate our measurements in this area. So we call that adaptive sampling. Self-maintenance. If the robots are out in the wild, one of them might fail. We want the robots to be able to diagnose themselves if they have a failure, come back to a base station for repairs, for example, and then redeploy into the network. And all of this should happen seamlessly without interrupting the performance of the whole network of robots. Environmental estimation, so we might want the robots to sit there and take their measurements of whatever they're measuring, talk to each other, and arrive at some conclusion about maybe the distribution of forest fire risk over the forest. Model learning and system ID is very much related to estimation, but a bit more sort of longitudinal, more related to machine learning. So perhaps they're in there taking data in the forest for a very long time, and we want to learn maybe a dynamical model of the evolution of forest fire risk as a function of time over the seasons. That would be a system identification or model learning problem. So these are the kinds of things you might want to do or might be interested in doing. And all of these are still really open research topics to some degree or another. So all those things that I mentioned we're going to formalize a bit more mathematically as I go through the talk. So beyond this environmental monitoring application, what might we use multiple robots for? What are the kind of application areas of multiple robots? Well, cleaning up oil spills or chemical spills. You can send a bunch of autonomous boats out to go vacuum up an oil spill, for example. Automated agriculture. You could imagine having drones look for moisture needs or pesticide needs over crop fields, and then another set of drones applying pesticide, and then a set of ground robots going and applying watering selectively, and so on. You can even imagine robots figuring out when crops are ripe, and other robots doing the harvesting, things like that. Infestation control, so you can imagine having the robots build a model of the spread of maybe a forest fire or maybe a pest infestation, and then apply maybe fire retardant or maybe pesticide to optimally steer or stop or retard the progress of those infestations. Disaster relief, you might have a big earthquake in San Francisco, people are trapped in the rubble, and you want to send a team of drones to go survey the rubble and figure out where the survivors are. Urban surveillance, so you might be interested in surveilling a sensitive area like an art gallery or a bank or whatever. Maybe you have a network of video cameras that are actuated, that can do pan and tilt, and so how do you pan and tilt them so that the entire art gallery is covered, or how do you follow an intruder as that intruder moves through the different frames of different cameras through a building. And then transportation systems is a big one now. Autonomous driving, so classically autonomous cars have been thought of as individual robots. You have one robot, lots of sensors on board, and that robot just has to get from A to B and not hit anything. Well, it turns out it's not so simple. When you have lots of autonomous cars on the freeway or on the city streets interacting with lots of human-driven cars and bicycles and pedestrians, you have to worry about the interactions, the dynamic interactions of those vehicles, and that's really a multi-robot problem. So why are we interested in distributed algorithms? So one of the main focuses in multi-robot systems is, in fact, distributed algorithms, although we'll talk in a little bit more detail about, is always distributed the right thing to do? Maybe do we want it to be centralized sometimes? So typically in this research community, people put a high value on fully distributed algorithms. If every robot can do what it needs to do using only its own information, and through all of the interactions of all of these robots you get some global behavior, some global desirable behavior, then that's considered a research success, right? And so firstly, why do we expect to be able to solve complex problems with distributed algorithms? And the answer is biology does this all the time. Biology is largely distributed at multiple levels of granularity. So if you think of an organism, I'm no biologist, that's not a secret, but I do know that organisms are made up largely of cells and scaffolding material that those cells create, right? And so the cells are the autonomous agents, and they're basically little machines, and they take signals, chemical and electrical signals, and they produce outputs like proteins and whatever, other electrical signals and other chemical signals, and the result of that is an organism. You and I, our consciousness, our ability to locomote, all of these things are essentially emergent behaviors of distributed algorithms operated by ourselves, which is kind of an extraordinary thing. If you think about us as a proof of concept of what's possible with distributed algorithms, it's pretty extraordinary. Now the state of distributed robotics, multi-agent systems, modular robotics, distributed algorithms, all of these research areas, the state of the art is, of course, vastly different from, vastly less impressive than this, than the human organism, obviously. But still, we know that there's a lot that can be done in a distributed setting. Not only are organisms themselves distributed, but organisms also group into groups with distributed features like herds of cows. My thing is not working here. Whoa, okay. Flocks of birds. You guys have all seen the videos of these starling flocks that kind of look like a fluid moving around in the air. Termites. So termites amazingly can build these incredibly large and elaborate nests. This is a termite nest. So in terms of scale, relative scale, the size of the nest to the size of a termite, these nests can be can be sort of the relative size of a skyscraper, like the Empire State Building or whatever tower you like to choose. And these things are built in a fully distributed way. Termites are fairly simple organisms. They bump into each other. They pick up morsels of soil, and they apply saliva, and then they put those morsels into the structure. And somehow through these simple interactions you have these incredibly complex structures. So it looks like a mound of dirt, but actually these things have incredibly complex passageways. They have ventilation systems and cooling and heating systems. If an anteater comes up and takes a swipe of this out of the side of this thing, they self-repair, meaning the termites will know that there's a problem and repair the structure. So all of this is done in a distributed way. People, the way that we move past each other in crowds is very much distributed, and shows lots of interesting structure, and we'll actually talk about crowd dynamics later on in the context of collision avoidance. And at a higher level, not only people moving physically, but just the way we organize ourselves in terms of political structures, economies, markets, the flow of ideas and beliefs and preferences. All these things are distributed and very complex, and also very effective if you think about the effectiveness of a market in allocating resources. So, okay, this is all kind of high-level, heady stuff. Let's talk about something a little bit more concrete. How do we actually model a robot, and how do we model a collection of robots? How is a collection of robots different from a robot? So a single robot, I like to think of abstractly as essentially a feedback loop with three components. So you have your robot, you have your environment. I'm showing this, forest sort of environmental monitoring scenario, but this is just meant to be the thing. This is meant to represent the thing outside your robot. It could be the freeway if you're talking about an autonomous car. It could be the building if you're talking about a wheeled robot moving around in a building, whatever. So you have the robot, you have the world, and the robot has onboard sensors with which to extract information from the world. Maybe cameras, maybe GPS, maybe LiDAR. It has computation on board, so ways of taking the information that is extracted from the sensors and reaching some conclusion based on that information. And it has actuation, so it has a way of producing a change in the world. Maybe that's just actuating itself, so moving around from one place to another. Maybe that's actually creating a change in the environment. Maybe there's a manipulator and you can move items in the environment. Maybe you can push items. Maybe you're interested in controlling a forest fire, and so the actuation is deploying fire retardant. In any case, this makes a feedback loop, right? This is basically a feedback loop. And so, as a control theorist, this is the way I like to think about things in terms of feedback loops. So how are multiple robots different from a single robot? Well, you obviously have multiple robots, and they share the same world, but there are multiple robots. They all have sensing, some way of extracting information. They all have computation. They all have actuation. This is all the same. There's one extra component, which is communication, or more generally, information exchange. So in multi-robot systems, the idea is that there's not one robot that has the full picture of the world or has all the data available to it. Instead, every robot has a local picture. If you have 10 robots exploring a building, every robot sees a different piece of the building. And then there's some way of exchanging information. Very often this is literally a communication network, like a Wi-Fi network or a Bluetooth network or a Zigbee network, whatever. But you have a communication channel. And oftentimes this communication network is such that not every robot can talk to every other robot. So information needs to be either hopped through multiple hops from one robot to another, or diffused somehow through local exchange of information. So this leads to the typical requirement of distributed algorithms in multi-robot systems. And when I say distributed, what I mean is the inputs to every robot are a restricted set of all the inputs in the environment, and also the actuation, the outputs that every robot can produce, are a restricted set of all of the actuations available to all the robots. So, so in robotics, you have the sensing side and the actuation side. And in the actuation side, you have a lot of ways of thinking about actuation. So I like to think of this in terms of a spectrum. You have sort of the decision-making, planning, control spectrum. And these are all, I like to think of these as a spectrum because they differ in flavor, but they aren't perfectly distinct. They kind of blend into one another. And let me give you an example of what I mean. So also, each of these is usually attacked with different mathematical tools. Each of these happens usually at different timescales. And for example, if you're interested in studying each of these, you would usually take separate classes here at Stanford. But my claim is that these are all kind of blurred together. They're all part of a continuum. So decision making would be the problem. So suppose we have a single robot here. We want to navigate this robot through some obstacles to one of 3 goal locations. So decision making, I claim, is this high level objective of where do I want to go? What's the goal choice? It's usually discrete. Oftentimes there's no explicit modeling of time or a time sequence. Or if there is a explicit modeling of time, it's usually very coarse. Usually it's a probabilistic setup, so usually modeled by an MDP or something like this. And oftentimes there's optimization involved. So I want to choose the best expected target based on some criteria. So then if you move along the spectrum a little bit, planning then is the problem of, okay, now I've chosen through decision making my target, maybe it's the square. Planning is the problem of how do I move the robot from here to here along some path. Now I haven't moved yet. It's the problem of how do I create a path mathematically before I start moving to get to that goal, avoiding the obstacles, right? So oftentimes this is related to optimal control. Sometimes it's discrete time. Sometimes it's continuous time. Sometimes the robot is modeled as deterministic. Sometimes it's stochastic. So this is kind of blurs the lines, right? We're starting to involve components of decision making and feedback control. Oftentimes the key considerations here are avoiding obstacles and being dynamically feasible, meaning that given the constraints, the dynamics of the robots, the things that the robot can do, I want to make sure that the path is such that the robot can actually follow it. And then at the far extreme of the spectrum is feedback control, which is, okay, I have my desired trajectory, I have my desired goal. How do I execute that trajectory? How do I move my robot along the path, keeping it along the path to get me to the goal? And so most commonly we model at this level with continuous time dynamics. It's usually continuous state. Usually, sometimes there's discrete time as well, but it's usually very short time scales. And the main consideration here is stability or convergence of something, right? So we're usually considering the stability of a closed-loop feedback control system or the convergence of some iteration to some desired steady state, some desired steady state configuration. So this class lies somewhere in this range. So very much focused on feedback control, especially in the early part of the class, and then later in the class we'll see more examples of planning. But it's certainly not decision making. So class content, mostly feedback control. Linear systems theory for stability and control. So oftentimes multi-robot systems are nonlinear. Sometimes they're linear, but it turns out that one of the fundamental distributed algorithms that we're going to be using is called the linear consensus protocol, and it can be analyzed completely with linear systems theory. And I will expect that you all have had a pretty in-depth exposure to linear systems and linear feedback control. So this would be classical feedback control and also state space feedback control. However, it turns out that oftentimes in nonlinear systems the analysis tool of choice is, oftentimes in multi-robot systems, the analysis tool of choice is Lyapunov theory, nonlinear stability theory. And I'll show you some examples at the end of lecture of why that is, why oftentimes when you're talking about multiple interactions between robots, you end up with a nonlinear system. So the first third of this course is going to be a fairly rigorous but fairly quick deep dive into Lyapunov theory and nonlinear stability theory. So we're going to derive the main theorem in Lyapunov theory. So the set of criteria that allows you to answer the question of whether or not an equilibrium for a nonlinear system is stable. We'll define exactly what stable means. For a nonlinear system, stability is a very much more nuanced concept than for linear systems. So if you've taken 209 here, Engineering 209, which is the nonlinear systems class, some of that will be review, although I approach the material a little bit differently than that class. But I know many of you have not taken that class. Out of curiosity, raise your hand if you've taken 209. Okay. So I think you guys will see a lot of things that are familiar, and hopefully you'll see it in a bit different way. But for those of you who haven't taken 209, the discussion in this class will be really self-contained. So it turns out that actually even linear, even in multi-robot systems, even when you have a linear model, oftentimes the nonlinear tools are just easier to work with for whatever strange reason. They just give you the answer in a more elegant way. So graph theory. So the predominant way that we model communication networks is through graph theory in this class. And if you're not, raise your hand if you know what I mean by graph theory or a mathematical graph. Okay, not everybody. So a mathematical graph, I'm not talking about graph paper. I'm not talking about drawing a curve with an x and y axis. I'm talking about a set of points and a set of edges that connect up the points. So it's a topological structure that represents networks and also represents many other things. It's just a topic from pure mathematics that has found lots of application areas, and modeling networks is one of the key areas. So this is actually one of the first topics we're going to start discussing next lecture is graph theory and how to connect graph theory with dynamical systems theory. So Bayesian estimation. So at the very end of the class, we're going to be talking about how you collect data with noisy sensors on your robots, and how you turn that noisy data into some kind of an estimate of something you're interested in, like the location of a target or the state of a map of an environment, and furthermore how you can do this in a distributed way. If you have multiple robots observing a target, how can they talk to each other and reach some agreement on what is the best estimate of where the target is? Okay, any questions so far? Still kind of high level, but I'm putting a little bit more meat on the bones, I think. Okay, so let's go into even more detail. Multi-robot systems, it's very much a living research community, so we have our own conferences. In any issue of a robotics journal, you're likely to find papers that are focused on multi-robot systems. So there's actually two different conferences. There's one called Distributed Autonomous Robotic Systems. It just happened back in October. And then there's another one called Multi-Robot Systems, MRS, which each of these conferences happen in alternating years. And then the big journals is Transactions on Robotics, Autonomous Robots, International Journal of Robotics Research, or the main robotics conferences like ICRA, International Conference on Robotics and Automation, IROS, International Conference on Intelligent Robots and Systems. So all of these things would have devoted sessions or devoted special issues or whatever under the theme of multi-robot systems or multi-agent interactions. So as a sort of research community, the literature you can think of as being divided into sort of current research topics. And these research topics are not very well defined, and they're constantly fluid. This is part of the complexity of a living research field, is ideas are constantly evolving, techniques are constantly evolving, and problems are at some point considered important, and at other points they go out of fashion, right? So what I'm going to show you here is trying to be a palette of what are or have been over the past 10 years the most common topics in multi-robot systems. So one of them is consensus. We're going to talk quite a bit about consensus in this class. It's a very simple problem at a high level, at least conceptually. The idea is you have a bunch of robots, so I'm showing these as physical robots, but this can be thought of more, more metaphorically as just states of computation in lots of different computers. So the purpose of consensus is to have these robots, through local communications, arrive at a meeting point and then meet at that meeting point. and then meet at that meeting point. So maybe you really do have physical robots that you want to meet at a meeting point, but that's actually not that common. That's not that interesting. Really, typically what's happening is you have lots of robots that are trying to agree on something. Maybe that something is the location of a target. Maybe that something is the presence or absence of a threat, whatever. So you have lots of distributed information. Every robot has its own piece of the pie, if you like, and through local communications, they want to arrive at a common agreement about the best fusion of their information is one way to think about it. Formation control. Turns out formation control, although on the surface it looks quite different from consensus, it turns out we can use the tools of consensus to analyze formation control as well. Formation control, you have a bunch of robots, you want them to move into a formation. Now, let me emphasize that many of these problems are only hard because they're distributed. This is obvious and easy if it's centralized. If I have one computer telling where the robots ought to go, then it's easy. You just say, okay, you go here, you go here, you go here. But that's not how it is. The scenario that I'm thinking of here is you have, say, lots of UAVs. Every UAV has its own local communication radius and its own GPS signal. And just by local communications over their local communication networks, they need to figure out how to arrange themselves into a circle, or arrange themselves into a 3D formation or whatever. So for example, you all probably saw in the recent Winter Olympics, what was that, a year and a half ago, there were these magnificent aerial drone displays of very large networks of drones moving into 3D formations like a snowboarder sort of cascading down the mountain. Do you guys remember those videos, right? So, well, one thing, those were pre-recorded. They were not live during the open ceremonies. They were pre-recorded at the site the day before when there was clear weather, or maybe a few days before, I don't know. But they were all done under controlled circumstances. But ultimately what they were trying to do is formation control. So I'm not only talking about circles here. I'm talking about potentially very elaborate and complex 3D sort of formation displays. So coverage and deployment. You have a bunch of robots. You want them to deploy over the forest to do environmental monitoring, or you want them to deploy over a disaster site to figure out where the survivors are. How do you make sure that every piece of your environment is being monitored by at least one robot? That's the problem of coverage and deployment. So you have some environment that you want the robots to collectively monitor. How do you get them to agree to order themselves in a way like this so that every piece of the environment is being seen? Target assignment. You have a bunch of robots. You need at least one robot at each target. How do the robots decide who goes to which target? So for example, if you have some survivors, you have your robots out monitoring your disaster site, and you identify 20 survivors, and you have 25 rescue robots. How do the rescue robots decide who goes to which survivor? You don't want all 25 going to one survivor, because then the rest of your survivors are out of luck, right? So collision avoidance, this is what we saw that video of with the cars in Hyderabad. How do you move the robots around so they don't hit each other? If you have an aerial drone delivery warehouse, you have some Amazon, we're talking 10 years in the future, Amazon has a warehouse somewhere in the Bay Area suburbs, and you have 10,000 drones flying out of that warehouse all the time. They better not be hitting each other as they fly out of the warehouse. Same thing, you have a bunch of autonomous cars in the city. They better not be hitting each other as they go through intersections. Communication aware control. So what if you want to talk to your neighbor robot, or many of your neighbor robots, but there's some obstruction in the way. So there's some fading in your communication channel because of a wall, for example. Can you use just the signal of the communication channel to improve without knowing explicitly where the wall is, but just knowing that there's a problem in your communication strength? Can you move the robot around to improve communication strength? And then finally, exploration and information gathering. You've got a bunch of robots, you want them to move around an environment to build a map of what's there. So for example, that you send all your robots through the door of an unknown building. You want them to explore the building and build a floor map of the building. So that's something like this. How do you coordinate the motions of the robots to build that map? So all these at a high level seem like completely different problems. And one of the things we'll be seeing in this class is that they're not really that different. when it comes down to it, there's always some element of distributed optimization in all of these problems. So you always have some way of representing the state of your robots. So in this case, just think of a simple planar example where your robots live in R2 or some subset of R2. Then you can always think of the state of your multi-robot system as one state in a higher dimensional space, right? Instead of having n states in R2, that is one state for each robot, you can think of one super robot or one concatenated robot, which is just a single vector in R to the 2n. And then oftentimes you can cast these problems that I'm talking about as optimization problems in this high dimensional state space, right? So oftentimes you have some cost surface, which maybe this is the, for example, the formation control problem, where a point up here means that the robots are very far from the desired formation. And a point down here means, okay, you've locked in that formation that we're trying to reach. And very often the geometry of these cost functions is non-convex. And that means that the optimization of these cost functions is inherently challenging. So one of the things we'll be seeing in this class is a kind of generic method for designing distributed controllers for problems like this based on gradient descent. And okay, if you're interested in sophisticated optimization in a centralized processor, gradient descent is probably not the right thing to do. So that's true, kind of, but then if you look at the giant boom in neural networks, what they do to optimize neural networks is actually gradient descent. So maybe a gradient descent isn't so bad after all. But anyway, as far as the state of the art in optimization algorithms, gradient descent is really stage one. It's a very simple algorithm. But it turns out that under this framework, if you use gradient descent, oftentimes you get a controller for each individual robot, and sometimes, under the right conditions, that controller depends only on the local neighborhood of that robot, and so it leads to a distributed control algorithm. And not only that, but under certain with certain assumptions, you can actually analyze the performance of that distributed control algorithm and prove that it converges to a local minimum or locally optimal configuration. And we'll see in this class that oftentimes these locally optimal configurations are good in practice. Even though they're not globally optimal, they're good enough in practice. So hopefully, going through the class, we'll see distinct multi-robot control problems, and then hopefully as things go on, we'll start seeing the commonalities of what otherwise looks like distinct problems. We'll start seeing them really more as individual instances of distributed optimization. And oftentimes we'll see that the algorithms that are proposed in the literature are just variations on gradient descent. So decentralization. I talked a lot about decentralization. It is kind of an implicit value of this research community. People like to see distributed algorithms. But it's not obvious that from an engineering point of view that the distributed algorithm is the one you want to use. Sometimes it's just easier and more cost-effective and more robust to use a centralized algorithm. And this is a living debate. There are partisans on both sides of that question, and oftentimes the research really lives on a scale from centralized to distributed. So oftentimes some components are centralized, some components are distributed. So by centralized, what I mean is you have a certain network structure where there's a base station, and that base station is connected to each individual robot. There's no connection among the robots, but each robot sends all of its information back to the base station. The base station does all the crunching and says, you go there, you go there, you go there, right? It's the kind of fully choreographed setup. Then the algorithm design is quite easy, but there are various other problems that arise besides algorithm design. And then the fully decentralized means that you have a network structure like this. Every robot is only talking to some neighbors. Nobody's in charge. There's some homogeneity or some equivalence in terms of the power or the authority of the robots, and they have to negotiate among themselves to reach some goal. So that's a really sort of 30,000-foot view of the state of the literature and the main topics we'll be covering in this course. Do you have any questions so far? Yeah?
It seems that they all focus on homogeneous
Yeah.
results.
So that will be the beginning assumption, absolutely. But as we move through the class, we'll see more and more examples of heterogeneous networks. And in the literature, you can find plenty of examples of heterogeneous networks. So it's just easier to build up the mathematics with a homogeneous set of robots. That's not to say that that's good, that we want only homogeneous robots. It's just to say that that's sort of a crutch that we lean on at the beginning, and then we'll see lots of examples of heterogeneity as we go on. Other questions? Okay. So I'll tell you a little bit about some of the research I'm doing in my lab. My clicker's not working. Okay, so I run the Multi-Robot Systems lab. I've seen many of your faces at my group meetings, so I know a lot of you know what we do in the lab. We do a lot of work with quadrotors. So this is an example of some of the planning and control that we do for quadrotors. Quadrotors are inherently nonlinear dynamical systems, so there is a challenge in just controlling them so that they follow a desired trajectory, and that's some of what we work on. Although most of what we work on is in problems of coordinating more complex motion among multiple robots, right, which is the topic of this class. So what I just showed you in that little vignette was a kind of formation control, dynamic formation control algorithm that we worked on recently. This is a variant of that algorithm where my student Ding Zheng has been able to, let me pause this, been able to fuse formation control with human-robot interactions. So basically you have an efficient way for a single human to command a large swarm of robots, and the human controls that swarm of robots as if it's just one individual sort of super robot, and then the robots then take care of themselves to avoid collisions and to kind of hold their formation as well as possible. We do some work with onboard vision and distributed control of vision. So here we have some quadrotors with downward facing cameras. You can see the fields of view of each of the cameras, and the robots are holding a formation using only the cameras. So they don't have GPS, they don't know where they are globally, they're just using their cameras and the overlaps in the field of view of the cameras to hold a formation relative to one another. This is a very tiny autonomous fixed wing plane that we built in the lab. Here's an example of a heterogeneous system and also a competitive scenario. So we have a ground robot. In this case, it's driven by a human. And the ground robot can hide in these, say, buildings or no-fly zones. And these are pursuit aerial robots that have to fly around, pursue this guy. And when he goes into a no-fly zone, they don't know where he is anymore, and they have to surround the no-fly zone to prevent him from escaping. We also do as much work outdoors as we can, although it's very difficult these days due to FAA regulations to fly anything outdoors. This is some work we did some years ago in a research forest in Massachusetts, where we deployed 5 quadrotors to autonomously do surveillance in a forest. And they were doing basically an environmental deployment algorithm called coverage control, something we'll study in this class. And here's the view of the camera from one of the quadrotors. So they flew out over a patch of forest that was about 1 kilometer by 1 kilometer to do monitoring over that forest. Okay, so those are some of our older projects. I'm going to talk about some of our more recent projects. So as I mentioned, we're interested in, lately, very much in sort of competitive scenarios. That means game theory. And in this case, in this line of work, we're interested in pursuit evasion. So the idea is we have 2 rogue agents. Maybe these are drones being flown by hobbyists over airports. So you probably heard in the news that Gatwick Airport was shut down for some time, causing tons of delays and potentially lots of safety concerns because of some knuckleheads that were flying their drones in the airspace. This is a terribly dangerous thing to do, but people do it. It's a real concern. So what if you have a fleet of drones at the airport that can autonomously go and disable these RC rogue drones, right? You can go up and it doesn't take much to get a drone out of the air. You just take another drone and hit the drones. They get tangled up and they fall to the ground. It's not a big deal. It happens in our lab all the time. So how do we do that? Bunch of pursuit drones. How do we get them to decide amongst themselves how to capture these 2 rogue drones? So we use a geometric approach based on Voronoi cells. You'll be hearing a lot about Voronoi cells in this class. And the algorithm that we propose is very simple. Basically, each one of these pursuit drones, if he shares a Voronoi edge, that's this line here, we'll define it mathematically much later, but shares a Voronoi edge with a evader or a rogue, then he moves to the center point of that Voronoi edge. This guy moves to the center point of that edge. This guy moves to that center point. This guy moves to the center point. The guys that don't have any Voronoi edges shared with a rogue drone, they can hang out, or they can move to the closest rogue drone that they want to move to. It doesn't matter too much. So how does this work? And then, right, everybody moves a little bit and updates the Voronoi diagram, moves a little bit, updates the Voronoi diagram. So it's a very simple algorithm, but what happens is that you get this really interesting emergent teaming behavior. The robots naturally form teams or coalitions, and they naturally sort of surround and trap the evaders into corners and then eventually disable the evaders. This is very easily generalized to 3D as well. So it's a really fast, efficient, and distributed algorithm, and it turns out we can prove theoretically that this will result in the capture of an arbitrary number of rogue agents in a finite time. So I can give you a time, 1 hour, after which all 6 rogue drones will be disabled. And in my lab, we like to put our money where our mouth is, so we like to not only design algorithms and do analysis, but to actually conduct experiments. So here's an experiment of this algorithm. The big guys are the pursuers, so these are the ones that are trying to capture the little guys, the evaders. And one of the evaders, the one in the red circle, is controlled by my student. I believe this was Zijan, one of my grad students. And so he has a bird's eye view of everything that's going on, and he was one of the designers of the algorithm of the pursuers. So he should, if anybody can avoid capture, he should be able to avoid capture. But he cannot avoid capture. So this is part of just a demonstration of the correctness of this mathematical guarantee that everybody will be captured eventually. In fact, he wasn't even the last one to be captured. One of the other autonomous evaders held out longer. So another thing we're interested in is coordinating without talking. So in the biological world, you see often, at times you see examples of large groups of organisms collaborating without any apparent way of talking. They don't obviously have voices, they don't have Wi-Fi. Ants is a prime example. Somehow there's ways to coordinate among agents that involve information exchange in subtle ways that are not as explicit as a Wi-Fi network, for example. So in this work, Zijan studied using small robots like ants to cooperatively move a comparatively large object. So the secret behind this is that, so typically to coordinate the forces of these ant robots, you would need to know the forces of your neighbors. So if this guy wants to push in a direction that is aligned with his neighbors, he would have to say, hey, which way are you pushing? Which way are you pushing? I'm going to push in a way that's somehow an average of your ways of pushing, right? But if there's no communication network, how do they do that? Ants don't have a communication network, and they do it. They don't sit there pushing against each other. Somehow their forces are aligned in such a way that they make progress. So the way that we propose to do this is look at the other side of Newton's second law. So Newton's second law, you have sum of forces is equal to mass times acceleration, right? So kind of high school physics. Well, you can sense the acceleration of the body that you're attached to. And then we also have some friction components. Suppose that we can sense the velocity of the body we're attached to, and we know the friction properties. Then we can measure the motion of the body, and then we can infer what are the sum of the forces being applied to it. And that gives us all the information exchange we need. And so that's what's going on here, is that we have one leader robot and 3 follower robots. There's no communication network. They're working together to move this box. And the leader robot, if he were on his own, he couldn't move the box. It's too heavy. And so the follower robots are feeling, with onboard force sensors, the motion of the box and then reinforcing that motion to help push the box along. We have also combined this with a form of online learning called adaptive control. So this is work by one of my students, Preston Culbertson. So how do you do cooperative manipulation like this if the robots, to begin with, don't know anything about the properties of the thing they're trying to manipulate? They don't know its mass, they don't know its dimensions, they don't even know where they are on the body attached, where they are with respect to the center of mass of the body. So Preston's work uses this form of online learning to figure out these properties in real time as control commands are given with this onboard camera. So each drone also has a little colored ball on top to make the computer vision a bit easier. But imagine the one drone is looking at the other drone with this image, and he segments where the ball is and then figures out how, what is the relative pose of his opponent drone using this segmented image. Both drones are doing this. So the only way they interact is through onboard vision. Okay. We have also extended this to cars. This is more challenging because cars have a nasty non-holonomic constraint, meaning they can't move instantaneously to one side or the other. They have to move along the direction of their wheels. And so this requires a completely different representation of trajectories and a very much different approach to planning. But the high level is still the same. The ego robot plans for himself, and then for his opponent, and then for himself, iterating until a convergence, and then you take one step. And so here the big car is slow, the fast car is, the small car is fast, and also the big car here was using a dumb planning method that was not our game theoretic planner. And the small car was using the game theoretic planner, and you can see that the small car is able to find an opportunity to pass the big car. Okay, so we've also done this on full-scale autonomous cars. This is a car that was developed in the lab of Chris Gerdes, who's a professor in mechanical engineering here at Stanford. It's called the X1. It's kind of a local Stanford test bed for autonomous driving and for vehicle dynamics. So this is Zijian Wang and Mingyu Wang, two students in my group, and they're driving in the X1, but the X1 is driving itself. They're just sitting there, monitoring the progress. And they're racing. This is the results plotted in MATLAB so you can visualize what's going on. They're racing against a virtual car because, of course, you don't want two full-scale autonomous cars to race against each other, not at this experimental level. You don't want these things to run into each other and cause lots of expensive damage and potentially hurt people. So we're racing a full-scale car against a simulated car. Okay. That is it for my little slideshow, and hopefully that gives you some flavor of what the current state of the work is in my lab and also what we're going to be talking about in this class. Do we have any questions or comments? I'm going to get started on the blackboard and give you a couple equations to chew on for the last 5 minutes. Questions? Comments? Yes?
Are class recordings posted online?
Good point, yeah. So Art is going to record all the lectures and post them with a 1-week delay, and they'll be posted on a password-protected YouTube channel. And the 1-week delay is to encourage everybody to come to class. Another thing that's going to encourage everybody to come to class is the fact that you have a certain probability every Thursday of being called on to lead a group discussion. So if you're not there, that group discussion is a graded component of the class. So if I call your name and you're not there, we will have to address that when we come to it, but hopefully you will all be here. If you cannot make a class on a Thursday, please let me know, and I will take you out of I will take your name out of the hat from which I will draw names, if that makes sense. But yeah, courses will be recorded so that if you are absent, you can watch the recorded course, the recorded lecture a week later. And if you need it sooner, just email Art and myself, and we can make it available sooner. Other questions? Okay. So we still have 5 minutes, which is plenty to get some equations on the board. Actually, this thing goes until 50 after. It goes until 10 till, so we have 10 minutes. How do I turn on those lights back there? Okay, that's good. Oh yes, I remember this room. All right, that's good. So it looks like the classroom scheduling gods have blessed us with a blackboard. I like blackboards. I don't know if you guys like blackboards. It makes me feel like I'm in the 1920s or something. Nice throwback. So it'll be fine for our purposes. So we're going to be starting in this class with very much a kind of control theoretic and dynamic systems perspective. So we're going to be thinking about robots, And oftentimes we'll be thinking about communication networks among these robots, maybe something like this. And this is a graph. So each of these things is called a node. Each of these things is called an edge. Usually we'd label the nodes with indices. So maybe this is node number 1, number 2, number 3, number 4. And this is going to be, say, edge 1, 2, edge 2, 3, and so on. We're going to get more into graph theory, how to represent graphs, and the kind of algebraic properties of graphs next lecture. So the graph, as I've drawn, typically represents the communication network, or the flow of information, the exchange of information. Then what's happening at each of these nodes is usually a dynamical system or a control system. So typically within each of these things we have a state, which we say x, and that state evolves according to some differential equation. And so hopefully you all are familiar with this kind of notation. This would be a typical control theoretic notation where we have the state xi. So you have xi dot is equal to some function of the state again and some control input. So this is all sort of typical notational conventions. Ui is typically the control input, xi is typically the state. Sometimes we'll think about homogeneous networks where this function f is the same for all robots. Sometimes we'll think about heterogeneous networks where we have f sub I, so f may be different for all the robots. So very typically, this function u, this is going to be our main interest at the beginning of the class anyway, is designing a feedback control law so that the collection of states does something desirable. Reaches a consensus, reaches a formation, avoids collisions with one another, whatever. So oftentimes we think of UI as defining some feedback controller, say G sub I, and that G sub I is usually a function of the state of the robot itself, xi, and its neighbors, the states of its neighbors, where we're going to use notation like this. So what do I mean by that? I mean, G is just some function. I haven't told you what it is yet. It's a function of xi, and then the states of the neighbors. So this is x sub j, where j is in the set of neighbors. What the heck do I mean by the set of neighbors? So the set of neighbors is determined by the graph. So for here, say n1 is some set of neighbors of node number 1. Even though we haven't formalized this in terms of graph theory yet, I think you can all tell me what are the set of neighbors of number 1. What are those indices, the neighbors of node 1? 2 and 3. So this just means that the control law for agent 1 can depend on its own state and the states of its neighbors, agents 2 and 3. So let's look at some very simple examples. This is a continuous time model, right? And that's actually going to be the kind of model that's going to occupy us for the first half of the class, so roughly. But we're going to see also discrete time models in the literature, certainly, and also later in the class we're going to be working with discrete time models. So continuous time model looks like that. Discrete time model looks like this. T plus 1 is equal to some function. These f's are not necessarily the same. Xi of t and ui of t. So continuous time, discrete time. A very common dynamical model that we're going to be using for robots in this class is called the single integrator model. So very simple model. Xi dot is equal to ui. What does that mean? That means that you have your agent here. Maybe this is a wheeled robot, maybe this is a quadrotor, whatever. And the way that it moves, so its state is xi, and xi dot is its velocity vector. So its velocity vector is something that you command directly. So this is velocity control. You're commanding the velocity directly. call this single integrator model. So we will use this model quite often in this class, and there's something that I want to be clear about is that this is not really a true dynamical model of any robot. No robot is truly a single integrator. Just by basic physics, we know that we cannot directly command the velocity of an object. We need to apply forces to the object and it moves through acceleration. However, the idea of a single integrator is that it's a good enough model, right? It's kind of sacrificing fidelity for simplicity. And typically the idea is that there's an underlying low-level feedback controller where that feedback controller tries to track a desired velocity. You apply a desired velocity and it very quickly produces that desired velocity. So this is a common way to model robots at this level. We can also think of a double integrator model, right, where UI double dot is equal to UI, where this is commanding the acceleration. So I don't know exactly how you want to show that. Xi dot and then Xi double dot. So you're not commanding the velocity directly, but you're commanding the acceleration directly. This is a slightly more high fidelity model. It really just models momentum, right? It models the fact that you can't instantaneously change velocity. We may occasionally be working with a common model for a differential drive robot, which is called the unicycle model. Which looks like this. Xi dot is equal to Vi cosine theta. Yi dot is equal to Vi sine theta. And theta I dot is equal to omega. Where, okay, the idea here is that your robot has two wheels, and those wheels can independently move, and so you can command a forward velocity for that robot V, but you cannot command a sideways velocity, right? It's on wheels, so it can't move like this. It can only move like this. But what you can do is spin the wheels counter to one another, and that produces a rotation rate omega. So the two control inputs for this model are V, the forward velocity, and omega, the rotation rate. And then you can see that the cosine theta and the sine theta, so theta here represents the heading angle, and that this encodes the non-holonomic constraint that the robot cannot move in this direction. So both of these models are linear or nonlinear? These two. Raise your hand if you think they're linear. Raise your hand if you think they're nonlinear. Okay, they're linear. They're definitely linear. We're going to talk about the difference between linear and nonlinear systems later, not in the 30 seconds that we have left in this lecture. They're both linear. Linear or nonlinear? Come on, guys. Yeah, nonlinear. You have these sines and cosines, definitely nonlinear. So there's going to be some challenges in dealing with this kind of model that won't be there when dealing with this kind of model. So these are the models of the individual robots. A very common technique for analysis is going to be to take these models of individual robots and put them all together in one big system. We call that the concatenated system or the joint system. And so maybe I didn't make it clear, but these x's are vectors. Xi lives in some space, maybe R2. If this is a wheeled robot on the plane, maybe Xi, the state of the robot, is just the position in R2. Or here, Xi is going to be, okay, so this is a bit poor notation, but this would live in R4. We don't worry about that too much at this point. This thing lives in R3. In fact, it's a little bit more complicated, but it's a three-dimensional state space. So what I'm trying to say is the x's are not scalars. Whenever I write a thing on the board like x or u, the default is that that is a vector quantity, unless I tell you otherwise. If it's a scalar, I'll tell you that specifically. Here, x and y are scalars. They're the x component and the y component, and theta is a scalar. It's the angle. But here, x is a vector, x is a vector, and u is a vector. So this concatenated system or joint system so the state is going to be just a stacked vector of all the states. Maybe you have n robots, lowercase n robots. The state looks like this, and so that means okay, let's also write the concatenated control input as a stacked vector of control inputs like this. So then what is the concatenated model for the single integrator robot? X dot equals what? Very simple. U. X dot equals U. What is the concatenated model for the double integrator robot? X double dot equals U. Same thing. For this one, it's a little bit more complicated, but that's okay. So the main thing I want to point out here is that we can model individual robots, and then once we've modeled individual robots, we can stick those models together and think about one dynamical system, one super robot living in a high-dimensional space, and we can think about analyzing the dynamics of that thing, which is all the robots stuck together. Right? Okay, I think that's it. We're done. Any final questions? Okay, cool. So next time we're going to talk about graph theory, and we're going to start talking about the linear consensus protocol. Okay.